Section 8.1, Graphing Systems of Equations. In this section, we are going to use the ideas we have used so far in graphing standard equations and graphing slope-intercept equations one step farther. Systems of equations means that we have more than one equation we are considering, and we are looking for any possible values that satisfy each of the equations. So here are two more equations. And since this is really a review of what we've been doing already, graphing linear equations, how about if you turn this off, graph these two equations on a piece of graph paper that you have, and then turn it back on again, and you can follow through my steps. Remember, after you graph them, you are trying to find the point where those two lines intersect each other, and that intersection point would be a solution for both of the equations. Okay, hopefully you've had time to go through and do both of these, find the intersection point. I'm going to do this fairly quickly. The very first equation, y is equal to negative 3x plus 6, is written in slope-intercept form. So I'm going to put a dot on 6, and the slope is a negative 3. So I'm going to go down 3, 1, 2, 3, and over 1 to the right. I'm going to go down 3 again and over 1 again to the right and put a 2. And I'll do it one more time, down 3 over 1. And that line looks somewhat similar to this. And once again, I'm going to try and draw as straight a line as I possibly can as I go through. The other equation that I have, x plus y is equal to 4, is written in standard form. So for that one, I'm going to make a table of values that x equals 0. If I do that, y is equal to 4. If I let y equal 0, x is equal to 4. So as I go through and plot that, I am going to have one of the points at 0, 4, and then the other point at 4, 0. And I'm going to go through and graph that line as well. Going through and graphing that line, I have a common point that satisfies both of those equations, and it is the point 1, 3, which means 1, 3 has to work in both of these equations. It works in this one if x is equal to 1, negative 3 plus 6 does equal 3, so it does work, and 1, 3 will work in the second equation as well. So the point that satisfies both of these equations is the point 1, 3, and systems of equations, that's what you are looking for. Is there a point that satisfies both equations? There are two other ideas in this section that we need to talk about. And once again, you can see I have two different equations. The very first one, y equals negative 2x plus 2, is written in slope-intercept form. So I'm going to put a dot on 2 on the y-intercept. And the slope is a negative 2, which means I'm going to go down 2 over 1 to the right. I'm going to go down 2 over 1 again. I'm going to do this several times so that I can have some different points. And I'm going to go through and I'm going to draw my line. So this line looks like that for negative 2x plus 2. For the other one, it's written in standard form. I have an x and a y for my t-chart. If x is equal to 0, y is equal to 4. If y is equal to 0, x is equal to 2. So I'm going to go through and I'm going to plot those also. I'm going to put a dot at 0, 4. I'm also going to put a dot at 2, 0. And I could use the idea of slope again, and I'm going to put in some other points that I know will work for that particular equation. I'm going to draw that line as well. Now, once again, realize I'm not able to use a ruler with this, so these are not perfect lines, but one thing that you may notice about these lines is that they are parallel. They are parallel lines, which means that they will never intersect. So, if you are doing systems of equations and you end up with two parallel lines, we give that a term, and we call that inconsistent. But really what it means is that there is no point that satisfies both of those equations. One other way that you could do this is that you could take a look at this particular equation and try to see, well, what's the slope of that particular equation? I know the slope of this top equation is a negative 2. If I have 2x plus y is equal to 4, and I'm going to do it down here, 2x plus y is equal to 4. And if I wanted to solve that for y, I would have to subtract 2x from both sides. If I subtract 2x from the left side, I have to subtract 2x from the other side, which means that I would have y is equal to that negative 2x plus 4. Y is equal to negative 2x plus 4. I'm trying to squeeze it all in here. But they have exactly the same slope. Since they have exactly the same slope, that means they're going to be parallel, and there is no point that satisfies both of those equations. Here's one final example. This time, both of the equations are written in standard form. So for the top equation, I'm going to make my t-chart, x and y. If x is equal to 0, I see y is equal to a negative 2. If y is equal to 0, x is equal to 4. So I can go through and plot these 2 points. Here's the point 0, negative 2. Here's the point 4, 0. And I can go through and draw my straight line for x minus 2y is equal to 4. When I go through and do the other one, also written in standard form, I'm going to set up my t-chart again with x and y. If x is 0, y is equal to a negative 2. If y is 0, x is equal to 4. Maybe you notice at this point that both of these t-charts are exactly the same. So when I go through and graph this second equation, I put dots again at the same spot, and when I draw that, I'm going to be drawing it on exactly the same line. What that really means is that both of these equations, 2x minus 4y is equal to 8, and x minus 2y is equal to 4, were really the exact same equation to begin with. They were just disguised in a way so that they look like different equations, but they are really not different equations. We can really show that these two equations were the same if we just take a look at the two equations and see what we have. That first one, x minus 2y is equal to 4. If I wanted to, I could multiply both of the sides by the same number. And if I chose to multiply both sides by 2, let's say I chose to multiply this side by 2, then I could also multiply this side by 2. Whatever I do to one side, I have to do to the other side. If I multiply the left-hand side by 2, I get 2x subtract 4y. If I multiply the right-hand side by 2, I get 8, which is the exact same equation as 2x minus 4y is equal to 8. If you end up getting something like that, where the two equations are really the same, and you find that out by graphing, you are just going to say they are the same line. They are called dependent. And every single point that is on that line is a solution for both of those equations because they are really the same equation to begin with. Section 8.1 is not really a lot of new information. It is just taking the ideas of graphing standard form equations and slope-intercept form equations and putting two lines on the same graph to see if they have a common point that satisfies both equations. If there is anything I can do to help as you work through this section, please be sure to ask.